Welcome to part 2 of the disinfection session. We are going to start with breakpoint chlorination. Now, the graph that you see here is it shows what happens when chlorine, either gas or hypochlorite, is added to water. First, between points 1 and 2, the water reacts with reducing compounds in the water, such as hydrogen sulfide. These compounds use up the chlorine, leaving no chlorine residual. You see where there's nothing left. The line is at the bottom there. Then, as chlorine is continued to be added between points 2 and 3, the chlorine reacts with organics and ammonia naturally found in the water. Some combined chlorine residual is formed, known as chloramines. Note that if the chloramines were to be used as the disinfecting agent, more ammonia would be added to the water to react to the chlorine at this point, and the process would be stopped at point 3. Using chloramine as the disinfecting agent results in little trihalomethane production, but it can cause taste and odor problems since chloramines typically give a swimming pool odor to water. In contrast, if hypochlorous acid is to be used as the chlorine residual, then chlorine will continue to be added past point 3. And between points 3 and 4, the chlorine will break down most of the chloramines in the water, actually lowering the chlorine residual. You can see it dropping there as it drops in these two, between points 2 and 3. Finally, the water reaches the break point, shown at point 4. The break point is the point at which the chlorine demand has been totally satisfied. The chlorine has reacted with all the reducing agents, organics, and ammonia in the water. So therefore, when more chlorine is added past this break point, the chlorine reacts with water and forms the hypochlorous acid in direct proportion to the amount of chlorine added. In other words, there's no more demand, so whatever chlorine you put in is available for disinfection. This point in this process is known as breakpoint chlorination. It is the most common form of chlorination in which chlorine is added to the water to bring it past the breakpoint and to create some free chlorine residual. And that's the point where you want your system to be at breakpoint, continually having that available chlorine. Okay. We are going to do more on breakpoint chlorination as well in the next lesson. Okay. So, factors influencing chlorination. As we already said, the pH is a factor, and chlorine disinfects better at lower pH. The temperature, the higher the temperature, the better. Turbidity, organic and inorganic matter. We know that the problem with turbidity is that little critters and bacteria and pathogens can hide behind suspended particles and solids. And also the amount of reducing agents in the water: hydrogen sulfide, ferrous ions, manganese nitrates, and ammonia. The more you have, the more it's going to influence your chlorination. So there you go. That is all we're going to talk about on chlorination. And we are going to move into UV ultraviolet disinfection. Okay. So I'm going to just read a little bit about UV radiation. It is effective against some bacteria and viruses, but it is not as effective against the relatively tough cysts and oocysts of pathogenic parasites. Consequently, it is used as a primary disinfectant only for groundwaters, not directly influenced by surface waters, where there is no risk of giardia or cryptosporidium contamination. Regulatory agencies will need to evaluate each situation where UV is proposed to determine whether it's appropriate. Okay. So, what we're going to look at some of the technology and the types of systems and lamps and the advantages and disadvantages of them. We're going to look at the operation of these types of systems and this type of technology, a little bit about safety, the effectiveness of the intensity, minimum UV dose calc and management, monitoring influent and effluent using PLCs, and then the maintenance of these lamps. It's a tricky thing. So talking a little bit about cleaning and defouling the lamps and how to dispose of them as well. Okay, so uses. So UV is biological, not chemical. There is no residual after, so it must be chlorinated after. And because of that, it does bring about some high costs, and they tend to be better used for a smaller utility. And one of the uses and benefits is that it does reduce some odor. Okay. Operation of UV systems. UV systems can be effective against some bacteria and viruses, but not for parasites. We mentioned that already. They are relatively simple to operate. There's no impact on the environment. They can take less space than other methods. They are, however, impacted by turbidity, color, suspended solids, and organic matter in the water. They create no trihalomethanes, and they are not effective for iron or manganese removal. And another disadvantage is that their bulbs can lose intensity and effectiveness over time. The most important maintenance procedure is to keep the lamp clean and replace it on a regular schedule so the minimum intensity required is always maintained. Some UV systems may be equipped with a shutdown switch if the lamp intensity drops too low. This would concurrently shut off power to the well. So UV, the setup of the lamps. The lamps are typically low pressure mercury lamps, mercury vapor lamps, and most typically they are multi-lamp assemblies, either vertical, as you see in this picture here, or horizontal. And if you've ever visited the treatment plant, the Santa Rosa Llano Road treatment plant, they do use UV disinfection, and their lamps look almost exactly like these ones here. I do recommend that visit if you've never had it. Okay, so operator's tasks. All right, operator's tasks. So it is important that the water in the depth of the channel stay consistent so that the lamps are submerged at that same level. They don't go too high or too low. So maintaining that water level. And then there will be process monitors to be able to check for the UV transmission as well. And that means that those monitors will look at the intensity of the lamps. And there's also monitor systems alarms for turbidity, the flow rate, gate operations, and power and level. So basically the operator would be probably looking at a control panel in a control room to look at these tasks. Maintenance of UV systems. Cleaning of the quartz sleeves is very important, and we've already discussed that. If they get cloudy or fouled, they're not going to be as intense and they're not going to be as effective. And additionally, changing the lamps as well. You know, all of these maintenance procedures would be on a schedule. They'd be on a timed sort of planned maintenance system. And then troubleshooting for poor performance. There may be a problem in the channels with short-circuiting or dead spots. That is typically a function that would be looked at in the design process. I mean, you wouldn't want to construct something and then later find out that it has dead spots. So hopefully you're going to catch that in design. Another thing that needs to be watched out is for biofilms that form on the channel walls and equipment. Again, that's fouling as well. And then also, if your water is turbid, then it could be shielding bacteria, so that has to be monitored as well. Okay, so that is all that I have on UV systems. Next, we're going to move into ozone. So we're going to look at how does it work, its effectiveness, its pluses and minuses, the equipment that's required, a generator and a contactor, ozone residuals, maintenance, safety, and then applications in the system as well. So, ozone is a very powerful oxidant used in treatment for color, taste and odor, organics, algae, cyanide, hydrogen sulfide, iron, manganese, heavy metals, detergents, and as a preliminary disinfectant. It must be followed with chlorination to provide a disinfectant residual in the collection system. Since ozone cannot be stored, it must be generated on site as needed. It is more effective than chlorine for viruses and bacteria. However, low doses can miss some viruses, pores, and cysts. Its action and its sort of implementation is way more complex than chlorine or UV. It has high capital and power costs, is not competitive with other methods. Ozone is very reactive, requiring non-corrosive containers like stainless steel. And it is not economical for water with high levels of suspended solids, BOD, COD, or total organic carbon. The operation of ozone systems. Ozone is produced when oxygen molecules are exposed to an energy source and converted to ozone. Dosing, mixing, and contact time are key to this process control. Disinfection depends on transfer of ozone in water. Other uses for ozone prior to coagulation could be treating iron and manganese, helping with flocculation, and removing algae. And there are other uses of ozone before filtration: oxidizing organics, removing color, treating tastes and odors. Equipment. Ozonation equipment has 4 components: a gas preparation unit that uses a commercial air dryer with a dew point monitoring system to produce dry air. Then the electrical power unit applies high voltage AC. And the ozone generator is a pair of electrodes separated by glass space and a layer of glass insulation. And then the contactor would be effectively the mixing chamber for ozone and water. It requires a monthly inspection of the electrical system and pressure vessels and lubricating parts, moving parts according to the manufacturer, plus a yearly inspection by the manufacturer. It is a toxic gas that's hazardous to plants and animals. This is ozone again. It irritates nasal passages in low dosages. It's less hazardous than chlorine since it is generated on site and not kept under pressure like chlorine. And its equipment has automatic shut-off devices for when hazards develop. Okay. Well, it looks like once again I'm going to finish this with part 3. So stay tuned for part 3. It'll be a short one. I just want to talk about your assignments, sort of related. to this test.